Okay, so now let's take this plot and well, this initial plot is how you would normally plot a spectrum where there's just a magnitude and the phase is 0. But down here we have a non-zero phase because it's complex. So let's plot it in a normal fashion. So this is, again, the spectrum representation, but more conventionally plotted. Representation. So for cosine omega t, we have, let's say it corresponds to this at omega 0. This is omega 0 t, and minus omega 0, we have amplitude 1/2. And we have amplitude here, which is conventionally the magnitude. Okay? So let's say it would normally be, let's say this is little x. Little x is defined as cosine of omega 0 t. So this would be the magnitude of x that we would normally plot. And the phase is 0. So we don't have to plot it. Now, for sine, for the sine, we take the value, so let's just note that capital X is the same because, maybe I should say, well, we've got it up here. You can still see it on the screen. All right, so there's the magnitude. The magnitude is the same. And so we would just plot that the same. But then the phase is not. So by taking the magnitude, we basically twist these things to point straight up. We're not playing any games with the angle. It's not a 3D plot anymore. It's now a 2D plot. And now we're going to need to plot the angle separately. And so what is the angle? Let's refresh our memory that we have minus j over 2 times e to the j omega 0 t plus j over 2 times e to the minus j omega 0 t. So what are the angles here? Well, at plus omega 0, we have a purely imaginary coefficient of minus j. We can forget about the 1/2. That's in the magnitude. So what is the angle of minus j? Make a little complex plane over the side here. So here's minus j. That's a minus 90 degrees. If we want to keep our phases between plus and minus pi, then that's a minus pi over 2, right? So we would have a phase of minus pi over 2 at plus omega 0. And then at minus omega 0, we have we can forget about the half. We have a coefficient of j, which is a plus 90 degrees, or plus pi over 2. So we would plot plus pi over 2 over here at minus omega 0. Here we are at plus omega sub 0, and 0 is in the middle. So, and another good question to ask me right now is, why do I have the urge to put arrowheads on the magnitude and not on the phase? And that is a real urge that I do have. And it's because in the Fourier transform world, the Fourier transform of a sine wave is actually impulsive. It actually goes to infinity. And let me not touch that page with this, but on a new page say that the Fourier transform, you can sort of see it from the definition, that if we were to go to the continuous time Fourier transform, it would be that capital X of omega equals the integral from minus infinity to infinity of the time domain signal x times e to the minus j omega t. And now everything is continuous. And so what happens is, you can at least see it blow up. Let x of t be defined as e to the j omega 0 t. so we're just fixing it at a particular complex sinusoid, then you can see that x of omega is the integral from minus infinity to infinity of e to the j omega 0t. Should I write this out in detail? I'll go ahead and write it out a little bit pedantically.
It might not be a terrible idea to talk about Dirac and chronic rectangle functions briefly.
Well, that's exactly what we're hitting. That's what we're going to run into right now. So this is e to the j omega 0 minus omega t dt. And at omega equals omega 0, you can see that it's equal to infinity. That much is clear. It's the infinite integral of 1. So the integral from minus infinity to infinity of 1 dt is equal to infinity. So that's why it blows up, and that's why we use arrowheads. But what's not so obvious is that it is essentially 0 everywhere else. So if I plot x of omega, let's say magnitude, as a function of omega, then at omega 0, sure enough, I get infinity. And so I need a little arrow to indicate that that's off to infinity. But it turns out that everywhere else, you can treat it as 0, even though the limit is pretty hairy. What it really is, let's say you start with a truncated integral. Let's say you truncate the integral, then what you'll see is basically a sinc function here. And as you let the integral grow to infinity, that sinc function will get narrower and narrower. Its oscillations will get faster and faster until, in the limit, the oscillations become dust. It just becomes stuff that you can't see under an integral. So when you take the inverse Fourier transform, you can't see it. All that dust is gone. We say that they are points of measure 0. The contribution to the inverse integral is 0. And that's just Lebesgue integration. If you want to study it, it's a cool topic. It's in the subject of real analysis. So get a book on real analysis and read about Lebesgue integration and points of measure 0. That's where this stuff all got nailed down and figured out mathematically. And it took a while. It took over a century, really, to nail all this down after the basic theory of Fourier theory was understood. So it was a very long, multi-century evolution of understanding. So this is the final end result. And it's hairy. And that's why we're not worried about it. That's why we're not doing it. And you never do it in practice either. We're going to do the discrete time case, and we never have any limits. We never have any infinities. And that's fine because they're not going to come up in the computer either. So mathematicians have to worry about this. We don't. But it's still theoretically useful. They're useful idealizations, and it's good to understand them and think in those terms. But the terms we need are that we have an impulse here that is infinity at omega 0 and 0 everywhere else. And there's one more property that we need to mention, and that is that the impulse has area 1. And that's because in the inverse integral, you want to get 1. So an impulse, the integral, and let me just go ahead and write this as delta of omega minus omega 0. That's the notation. So we're not going to deal with this, but I just want to say it once, and that is that the integral of the delta function, since we're in omega, let's keep it there. The integral of a delta function from minus infinity to infinity is equal to 1. And so it's also true for any shifted impulse. If we shift it out to omega 0, we can plot it out like this. So we have this, we have the shifted impulse. That's going to be 1 too. It doesn't change anything to shift it around. So it's this idealization. It's this infinitely thin, infinitely tall rectangle of area 1. And its property is that it samples integrals. It's an integral sampler. And you also need this in deriving sampling theory. If you really want to start with a continuous function and sample it and then prove the sampling theorem, you have to deal with this stuff. But we won't have to deal with that in this class because we're doing the DFT. And so we can always get to this by taking a limit. As the DFT length goes to infinity, we can always get ourselves in this kind of, impulse hot water if we want to get there. But in practice, you never do. So it's only there if you are interested in it. But it's still a useful idealization that the impulse is an integral sampler. They call this the sifting property. So then in particular, if you have some continuous function, f of t, and you multiply it by an impulse at t0 and integrate from minus infinity to infinity, the so-called sifting property is that the answer here, I need a dt. The answer here is f of t0. So you can multiply a function by a delta function at any point, integrate, and get the value of the function at that point. Now, this is, of course, for a well-behaved function. So let's just say f is continuous to keep it reasonable. So that is the sampling thing. So if you have a continuous function, this is how you sample it mathematically. If you want to try to prove the sampling theory, the sampling theorem, then what you'll do is take a continuous function and multiply it by a sequence of delta functions or impulses, shifted impulses, at time 0, at time t, your sampling interval, at time 2t, and 3t, and so on. And that will sample the function for you. And you can't really do it any other way because if you just take the value, you don't have something you can write down in a form that can be analyzed. Because you need to be able to now take the Fourier transform. So you need to sample under the Fourier transform in order to prove that the sampling can be converted back to the original signal. Because the constraint is that the bandwidth be less than the sampling rate. We like to say that the sampling frequency is twice the highest frequency in the signal. So now we're in the frequency domain. So we have some band-limited signal where the signal has to have 0 energy above half the sampling rate. But what's more fundamental is to say that the total bandwidth of the signal fits in the total bandwidth of the sampling. So if you think of both positive and negative frequencies, then what it is that the bandwidth of the signal is less than the sampling rate. And that is the right way to say it for complex signals, because for complex signals, you have now independent negative and positive frequencies. And so if you sample a complex signal, then you can't say that, you can't just talk about the positive frequencies or the negative frequencies. So it's better to just talk about the band spanned by the signal. And then that also will work for bandpass signals. So if you have some band of energy at some high frequency carrier zone, then the sampling rate has to exceed the bandwidth of that band. So that's why, the usual statement is sort of constrained. The better statement is that the sampling rate exceeds the bandwidth, and it's more natural. And then to prove that sampling theory works, you have to then show that you can reconstruct the continuous signal from these samples obtained in this way using the band-limited property. And that's actually a bit of work, and it's something we can do probably pretty easily at the end of the quarter, but I wouldn't want to try to do it now, really. It would be easier at the end of the quarter. It'd be a nice way to kind of see some of the fundamentals in action in the continuous case. It'd be a nice review and extension. So did I finish that well enough? So spectral representation. Yeah, so we added we did the magnitude and phase plot for the sine wave. For the cosine, it had a 0 phase, and so we just need the magnitude plot, which coincides with the amplitude plot. So you have a real spectrum. And this is a Fourier theorem that I previewed, that every real and even signal has a real and even Fourier transform. Cosine omega t is our first example. So it's a real function and it's an even function, meaning that cosine of minus is cosine. So cosine of minus theta is cosine of theta, so it's an even. It's invariant under left-right reversal. And so that means its Fourier transform is real and even. That means its phase is 0. That means its amplitude, well, its amplitude equals its magnitude unless it goes negative. So it could have a negative amplitude and be real. So, so it's not always true that the magnitude equals the amplitude. But to within a minus sign, it is. So I was saying I could show you why e to the j omega t falls out as the fundamental single frequency thing. And I really did kind of set it up well with the delta function already, because that is what that's basically it. I mean, the answer is just sitting right in there. So I defined the Fourier transform. I set x to a single frequency sine, what I claim to be a single frequency sine wave. And you see that only for that value of omega does it blow up. So that's basically what I was going to show. And you can see that if I made it e to the minus j omega 0 t, then I would blow up at minus omega 0. So you really do get that difference between omega 0 and minus omega 0 that the impulse moves. So that is seeing positive and negative frequencies in the Fourier transform. And if I were going to derive it completely, I would do it in the discrete time case. So I was actually, before the break, I was thinking of doing it in the discrete time case where I could really get all the answers explicitly instead of just waving my hands about impulses and infinities and points of measure 0. That was more of an advanced aside, but it works out the same. I mean, the structure of it is exactly this. That's what will come out, but it would be using sums, and we would get closed form formulas that are exact and no impulses. But we would get sinc function things that do approach those impulses in the limit. So if you let the sampling density go to infinity, then you get your impulses. Don't know what to talk about?